Hello everyone, welcome to my group theory lecture. In this lecture, we continue to study Lagrange's theorem. Last time we proved the following theorem here, which says that an equivalence relation R on a set S partitions the set S into equivalence classes. And the set of all equivalence classes, right? We denote it by this notation S mod R, and this is called the quotient set of S modulo R, or in short, S mod R. And later on, we are going to study that, like I mentioned the last time, for a particular type of, the equivalence relations, right? We can turn this quotient set into a quotient group. So we will talk about that later, right? In fact, I mentioned what type of those equivalence relations are. Those are something called the congruence relations. And what are the congruence relations? Equivalence relations that preserve operations. Okay, so we are going to get back to that later on. So now we are going to move on to this. So the converse of the preceding theorem is also true. Okay, so previously what we studied was, when an equivalence relation is given on a set, that equivalence relation partitions as. Conversely, when we have a partition, okay, we can also, the equivalence relation from the partition. So here's the statement. Okay, so here class P is a collection of these sets AI. So A sub I. So this is a partition of a set S. Such well, what that means, the partition means again, and the previous theorem, right? So those two, 1 and 2, these actually define the partition, a partition on a set. So this class is a partition of a set, which means that the union of all these classes is the entire set S, and for any INJ, two different INJ, AI and AJ is empty. Okay, so those partition members, okay, those classes, are pairwise disjoint. Okay, pairwise disjoint. So in this case, we define a binary relation R on this set S by the following. Okay, so for any A, B, two elements in S, A is related to B if both A and B belong to the same class for some I. In this case, R is an equivalence relation on S called equivalence relation induced by the partition P. This is easy to prove, and so I'm not going to prove it. This is left for an exercise. In fact, the proof of this theorem is part of the problem set, I believe, number 4. Okay, so you will find out. Moving on to next. Okay, now so here's an example. Let f from x to y be a surjective map, onto map. Then f inverse of y such that y belongs to big Y forms a partition of x. What we have here is, that's the inverse image of f, right? The inverse, inverse image of f. In this case, the equivalence relation induced by this partition is the following, okay? Kernel of F, so that's the notation for that, right? That's a set of ordered pairs A, B in X Cartesian product X such that F of A equals F of B. This equivalence relation is called the kernel of the function f, okay? Now, later, we are going to revisit this, the kernel of a function, okay? Because in group theory, okay, this kernel can be represented, okay, in a different way as a particular type of subgroup, which we call a normal subgroup. And later on, I'm gonna discuss the cross relationship with this definition of a kernel of a function and the kernel of a kernel in group theory. Okay, as something called a normal subgroup. Very important notion. Let me prove this right before we continue. Okay, so what I have to do here is to prove that in fact this inverse image, right, f inverse of y, okay, the inverse image forms a partition of x, right? The rest comes from previous theorem, right? So let's go to my notepad. Example, set of f inverse of y such that y as in y we talked about this in my very early lecture, one of those, right? This can be simply denoted by f inverse of a big Y, okay? That's called the preimage, okay? The inverse image, not the preimage. I think that's preimage. Y under you might say inverse image also. I think that's fine too. Under the function f from x to y. Also, I'm gonna also use, yeah, you can also say inverse image. So we want to show that this forms This forms a partition, a partition of X. Okay, a partition of X. Proof. So first we want to show, okay, so we want to show that X is the union of F inverse of Y. Okay, F inverse of Y, here Y, little y is in the codomain, big Y. Okay, so here, this part is clear, right? This part is clear. Because each F inverse of Y is, the subset, okay? Each F inverse, I mean, the, yeah. So each class, right, each class F inverse of Y is a subset of X. So, the union of all those subsets are also, the subset. So, this part is clear. So all we have to do is to show that, show the other way around, right? So oh, let X belong to X, okay? X belong to X. Then Y equals F of X belongs to Y because, F is a function, right? And that implies X belongs to inverse, the inverse image or preimage of Y. Okay, of course, what that means is X belongs to union of all these guys, right? So union of all these guys. So we are done. So that means so X is a subset of this guy here. So by combining these two, we just showed that this is the same thing. So the inverse image, right? So the the inverse images, F inverse of Y, right? They cover, right? So in that case, we use the word cover. They cover X, right? So now we are going to show the second part. Okay, second part. So now let y1 and y2 be two different elements in y. Okay, in y. And we want to show that, so here we want to show that f inverse of y1 intersection f inverse of y2 is empty, right? So they are disjoint. But I'm going to prove this, by contradiction, okay? By contradiction. So suppose so that's what I want to show, but I want to prove this by contradiction. So we suppose the contrary. Okay, so f inverse of y1 intersection f inverse of y2 is not, okay, we are assuming that it is not empty. Then, of course, what that means is there exists, right? Now you are familiar with this notation, right? There exists at least one element in this intersection. Okay, so f inverse of y1 intersection f inverse of y2. And that implies that y1 equals f of x and y2 equals f of x also. Okay, so in other words, here, the same element x is corresponded to two different y values, y1 and y2. Okay, these are different. This is a contradiction because f is a function. Okay, right? For the function, this does not happen, right? So this is a contradiction to contradiction to the fact that f is a function. Okay, f is a function. Hence, f inverse of y1 intersection f inverse of y2 must be empty. Okay, empty set. So done. So we finish it, proving it. Okay. So let's get back to my slides. All right. So here's a lemma. Let G be a group and H be a subgroup of G. And also let R be the equivalence relation on G given by for any A, B in G, A is related to B if A, B inverse is in H. Okay, I think I defined this equivalence relation. So let me go back and quickly check. I did. Okay, so we talked about this already, right? So I remembered it correctly, right? So I don't have to talk about this. I do believe that I proved that this binary relation is an equivalence relation on this group G. So let's get back. Here, that's the statement for this lemma. For each A element A in G, the equivalence class of A happens to be is the same set as H times A. What is H times A? It is defined by the set of little h times A such that H is in this little h is in big H. This set HA is called a right coset of H in G. Okay, so let's prove this. I'm gonna need a new page. So here's lemma. So we have a relation R. Okay, so for any two elements A, B, A is related to B. Okay, so here, so G is a group and we have H, right, a subgroup of G. So A is related to B if, okay, if A, B inverse is in H. All right, so that's we proved it, right? We proved that this is an equivalence relation. So what we want to show here is that for any, right, then for any A in H, sorry, G. The equivalence class of H is same as HA, right? So that's what we want to show. By the way, again, right? So here, this R is an equivalence relation, right? Equivalence relation on G, okay, right? So we proved earlier, right? We proved it. Here, you know, the HA, which we call, you know, a right coset of H, right, in G. This is defined by set of little h times A such that little h is in the subgroup H. So here's proof. So as usual, you know, we're trying to show that two sets are the same. So, you know, one set is a subset of the other and vice versa, right? So that's how we are going to show. So first thing is, right, so we show that the equivalence class of A is a subset of HA. Okay, that's what we want to show. So what do? We start with picking an arbitrary element B, let's call it B, from the equivalence class of A, right? So that implies, of course, by definition, B is related to A, right? And by, again, definition of the relation, this means, you know, the B, A inverse is in H, right? Okay, and that means BA inverse, right, is we can actually call it little h, right? Little h. So for some, what this means is for some, so BA inverse equals like little h, one of those elements, right? For some h in h, right? Has to be same as one of those elements. So now, you know, we multiply uh, this whole thing BA inverse equals H by H from the right. Okay, then we have B equals A H, right? Oh, sorry. I said from the right. Okay, so that's gonna be HA. Okay, but then this is what? This is this belongs to the right coset HA. So we just showed that this is a subset of HA. Okay. In fact, we can actually also go backward, right? We can actually also go backward. So in order to show the other way around, so the HA, the right coset HA is a subset of the equivalence class of A, we pick an element, right? Okay, we pick an element B. Yeah, I think I better actually write that down. Okay, I was just trying to be a little lazy, but yeah, I guess I better do that separately. Okay, so go ahead, no big deal. So now this time we show that. So here, right. Thus, we just showed that class of A, equivalence class of A, is a subset of right coset HA. Now, we now show the other way around, right? Okay, show that HA is a subset of the equivalence class of A. Okay, that's what I am going to show. So this time pick any, pick an arbitrary element B from, this right coset H sub A. That implies that B can be written as little h times A for some H in the group, subgroup H. So, here now what we are going to do is multiply B equals H times A by A inverse from the right. So we get B inverse A equals H. Now this little h is an element in H, right? So this means B inverse A belongs to H. So by definition, B no, something I did it, sorry, I did it incorrect, not B inverse A, B A inverse, right? That's B A inverse. So B A inverse. So that means B is related to A by definition, right? Okay, and what does that mean? Since B is related to A, B must belong to the equivalence class of A. Thus again, so in this case, H A is a subset of the equivalence class of A. And therefore, the equivalence class of A equals the right coset HA. Okay, so we completed the proof. All right, so here's an example, right? So we consider this, very important example actually, right? So I emphasized a lot last time. This is the one of the right the, the typical example, one typical example of the so-called congruence relations. Okay, so the uh, equivalence relations that preserve operations. So here consider this congruent mod n, right? And so in this case, with this equivalence relation for each A, the equivalence class, okay, the equivalence class of A is, given by n times C, okay, n times C plus A. So you might be thinking, oh, this looks like a little different. No, it is not. Now, first, right, it is automatically. We didn't say anything about like the subgroups, right? Okay, but actually, we talked about that earlier. The additive group Z with plus, right? Okay, the additive group Z has the all subgroups of the additive group of Z, um, sorry, the all the subgroups of the additive group of Z is given by this type, right? So little n times C, okay? So we talked about that earlier. And here, that since the binary operation is not multiplication but addition, so coset instead of given by like h times a, here in this case actually h plus a, so it takes this form. So it looks a little different, but no, it's the right coset. So the right coset nz plus a is called the congruence class of a modulo, or I should make a space here. The congruence class of a modulo n, okay? A modulo n. So there should be space between a and modulo. I'll fix that later. All right, I think I'm gonna stop right here, and we'll continue. Okay, in my next lecture. So we are actually now ready to talk about the main topic here, Lagrange's theorem. Previously, or that we talked about is basically like a background to discuss Lagrange's theorem, right? Uh, where equivalence, the notion of equivalence relations and equivalence classes, play crucial, crucial roles. Okay, so we will get back to this. Thank you.